Good morning, friends. Hello, I am Dr. Sunita Tandon from RR College, Alwar. Today, I am going to deliver lecture number 3 of MSc Final Semester 3rd Environmental Chemistry of Unit 4. Now, today we will learn wetlands and wealthlands and chemical composition or acid-base chemistry of seawater. The wetlands are areas of submerged or water saturated lands, natural or artificial, static or flowing, fresh or brackish, saline including areas of marine water, and depth of which at low tide does not exceed 6 meters. Wetlands include ponds, lakes, rivers, streams, marshes, reservoirs, mangroves, and marine water of shorelines. Chemical composition of wetland, namely lake, rivers, and stream, is described earlier. Now we will study the chemical composition of seawater. The marine ecosystem includes seas, oceans, bays, and estuaries. Sea and oceans cover about 70% of Earth's surface. They have a volume about 15 times greater than that of land. Seawater contains 0.5 m NaCl and 0.05 m magnesium sulfate alone with magnesium chloride, K2SO4, calcium carbonate, and traces of all conceivable matter in universe. An estimate showed that the whole sea contains enough salt to cover the continents with a layer of 100-meter thick. The elemental composition of seawater can be seen in table number 2. It contains sodium as sodium ions, potassium and potassium ion, magnesium and magnesium ions and magnesium sulfate, calcium as calcium ion, calcium sulfate, barium as barium ion, barium sulfate, iron as iron hydroxide, zinc as zinc ion, zinc sulfate, copper sulfate, nickel as nickel sulfate, Mn as Mn plus 2 nickel sulfate, vanadium as VOH2 hydroxide, OH, cobalt is cobalt ion, cobalt sulfate, cadmium is cadmium ion and cadmium sulfate. Seawater contains about 2000 times more dissolved salt than fresh water. The most abundant element, except hydrogen and oxygen, namely sodium, chlorine, magnesium, constitutes 90% of matter in seawater, while potassium, calcium sulfate exhibits 3% and other elements 7%. The seas and oceans are the final sinks for many substances involved in numerous geological processes. Ocean waters are more or less well mixed, with the result that it contrasts to the variable composition of freshwater bodies. The ratio of major constituents of seawater are almost the same all over the globe, although the salinity is variable from place to place. The elemental composition of seawater with principal chemical species is illustrated in table 2, which I have told you earlier. Other chemical species occurring in seawater constitute lead plus 2, lead sulfate, cesium plus 2, vanadium plus 3, silver chloride minus, Cl minus, SO4 minus, HCO3 minus, H2CO3, BOH whole thrice, HASO4 minus 2, H3ASO3, and organic compounds, etc. Now we'll study the physical chemistry of seawater. Seawater chemistry is extremely complicated since it deals with a system having unconventional parameters such as average temperature 5 degree centigrade 0 to 30 degree and pressure of 200 atmosphere at the surface and 1000 atmosphere at the bottom. It is estimated that oceans have undergone about 0.5 million rotations during 500 million years, assuming a rotation period of 1000 years. This indicates that the liquid phase has been thoroughly mixed. The constant interaction of seawater with atmosphere, biosphere, sediment involve unique dimensions of the equilibrium process. Now, seawater equilibrium. Following parameters should be considered to understand seawater equilibrium. First is pH. The constant pH of seawater is 8.1 plus minus 0.2. All over the world is complicated to explain. Possible mechanisms involved are buffering action of BOH whole thrice and BOH4 minus system. Second है buffering action of H2CO3 HCO3 CO3 system. Carbon dioxide combined with water to form H2CO3. It gives one proton to form HCO3 and it again gives one proton to form CO3 minus 2. Third is ion exchange equilibrium of dissolved cations with silicates of marine sediment. 2 potassium ions plus 2 calcium ions, 2 Al2 Si2O5 OH4 solid plus 4 SiO2 solid plus 9 water molecules gives 2 potassium calcium Al2 Si5O16 H2O6S and 6 H ions. Ion exchange equilibrium seems to be the major buffering factor in the seawater. Second is PE. Just as pH is defined as the negative log of hydrogen ion activity in aqueous solution, pH is equal to negative log of H ion concentration. Similarly, PE is defined as the negative log of electron affinity in aqueous solution. PE is equal to minus log of activity of E negative electron with negative charge. The thermodynamic definition is based on the reaction 2 H ion of aqueous mediate take 2 electrons to form hydrogen gas. The free energy change for this reaction is exactly 0 when all components of the reaction are at unit activity. This reaction forms the basis for the free energies of formation of all ions in aqueous solution and also defines the free changes for redox process in water. Now, PE is somewhat difficult to visualize than pH. Consider pure water at 25 degrees centigrade is a medium of 0 ionic strength. Activity of H ion is equal to 10 to the power of minus 7 and pH is 7. But activity of electron affinity is equal to 1 and PE is equal to 0. When H ion aqueous at unit activity is in equilibrium with hydrogen at 1 atmospheric pressure, if the electron affinity is increased 10 folds, then activity A of AE is equal to 10, PE will be minus 1. The relation between PE and electrode potential E may now be visualized. Note that PE is the negative log of electron affinity but not the negative log of electron potential. It is negative log of electron activity but not of negative electrode of electrode potential. According to Nernst equation for electron potential, E is equal to E0 plus 0.0591 upon N log of reductant upon product, reactants upon product at 25 degrees centigrade. From thermodynamic considerations, PE is equal to E upon 0.059 at 25 degrees centigrade. The Nernst equation becomes PE is equal to PE0 plus 1 upon N log of reactant concentration upon product concentration. At 25 degrees centigrade, PE is equal to E upon 0.591 and PE0 is equal to E0 upon 0.0591. These are standard values. Now consider some typical reductant half reactions with standard electrode potential E0 and PE values. Copper takes 2 electrons and converted into copper. E0 for this reaction is plus 0.336 volt and PE0 for this is 5.71. Similarly, for 2H ions plus 2 electrons gives hydrogen gas. E0 for this reaction is 0 plus 000 volt, and PE0 is also 00. Lad2 plus 2 electrons gives you Lad0. E0 is minus 0.26 volt and PE0 is minus 2.14. The redox reaction with more positive E0 or PE0 value will proceed more readily than the one with lower value of E0 and PE0. Hence, copper has a greater tendency to interact with electrons than lead. 2. Thus, lead metal gets coated with copper when placed into a solution of copper. Lead plus copper ions will give you Lad2 plus copper. PE values in natural aquatic system, redox reaction in natural waters. The limits of PE in water are established by the following reactions. First is 2 water molecules, they are converted into by reversible reaction into oxygen plus 4 H ions plus 4 oxygen electrons. This is de-electronation, so therefore it is oxidation reaction. In the second reaction, 2 water molecules takes 2 electron and is converted into hydrogen and 2 OH ion, and this is reduction reaction. The oxidizing limit of stability of water is expressed by the equation 1 upon 4 oxygen plus H ion plus electron will give you 1 upon 2 water molecule and PE0 value of plus 20.75. Therefore, PE is equal to PE0 plus log of PO2 raised to power half into hydrogen ion concentration. PE0 is equal to 20.75 minus pH. In aerobic neutral waters, PE is equal to plus 13.75 and PO2 is equal to 0.21 atmosphere. In anaerobic waters, CH4 and CO2 are produced by microbes. Assuming pH is equal to 7 and PCO2 is equal to PCH4, PE is equal to minus 4.13 and PO2 is equal to 10 to the power 17 to atmosphere. In seawater, PE is calculated by equilibrium with atmospheric oxygen 25 degrees centigrade and zero activity. Half oxygen gas absorbs 2 hydrogen ions and 2 electrons and is converted into water, and log K is equal to 41.56. Log K is equal to log H2O minus half log PO2 minus 2 log H ions minus 2 log E. This is equal to minus 0.01 minus 1 upon 2 log 0.21 plus 2 pH plus 2 PE. This is equal to minus 0.01 plus 0.34 plus 16.4 plus 2 PE. Therefore, PE is equal to half 25 is equal to 12.5. For seawater, this value of PE does not fluctuate with small variation of pH and oxygen content. Thank you, students. This is our third lecture and we will study about seawater model in our fourth lecture.